Good morning, students. In this class, I would like to explain about eigenvalues and eigenvectors. Introduction. Eigenvalues and eigenvectors are important concepts in linear algebra. They are derived from the German word eigen, which means a proper or characteristic. Eigenvectors are non-zero vectors that get mapped into scalar multiples of themselves under a linear operator. Definitions. Let A be any square matrix and lambda be any eigenvalue and I be the identity matrix which is based on A. So A is a square matrix, lambda is eigenvalue and I is identity matrix which is based on A. Then we have A minus lambda I is called characteristic matrix. Determinant of A minus lambda I is called characteristic polynomial. Determinant of A minus lambda I equal to 0 is called as characteristic equation. So A minus lambda I is characteristic matrix. Determinant A minus lambda I is called characteristic polynomial. Determinant A minus lambda I equal to 0 is called as characteristic equation. Now definitions of eigenvalues and eigenvectors. Characteristic roots or eigenvalues. The roots of characteristic equation is called as eigenvalues or characteristic roots or latent roots or proper values. So characteristic equation means determinant of A minus lambda I equal to 0, whose roots are called eigenvalues or characteristic roots or proper values. Now characteristic vector or eigenvector. A non-zero vector x is said to be eigenvector of A if there exists a scalar lambda such that Ax equal to lambda x. So here there exists a lambda which satisfying the equation Ax equal to lambda x, then x is called eigenvector. Let us see example. Example 1. Let A equal to matrix of 5, 4, 1, 2. So it is a 2 by 2 matrix and X is a matrix of 1 minus 1. It is a 2 by 1 matrix. Then consider AX, just multiplying these two matrices, 2 by 2, 2 by 1. Result is a 2 by 1 matrix. 5 ones are 5, 4 into minus 1 minus 4, 5 minus 4 is 1. 1 ones are 1, 2 into minus 1 is minus 2, 1 minus 2 is minus 1. So it is matrix of 1 minus 1. It can be written as 1 into matrix of 1 minus 1. Now clearly this is of the form Ax equal to lambda x. But what is lambda here? 1. So here x is, that is eigenvector is matrix of 1 minus 1 and corresponding eigenvalue is lambda equal to 1. Another example. Suppose matrix of 4 1 is an X matrix. Now consider Ax. So similarly we have lambda x. So that is, what is lambda here? Lambda is a 6. So eigenvalue is a 6 here and the eigenvector is 4 1, matrix of 4 1. So Ax equal to lambda x, then lambda is called eigenvalue. Equation satisfying vector x is called eigenvector. Problem. Find the eigenvalues and corresponding eigenvectors of the matrix. Matrix of 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3. First of all, we define the matrix A. Now we will find the characteristic equation of A. The characteristic equation of A is determinant of A minus lambda I equal to 0. So taking the determinant of the matrix A and subtracting the elements, principal diagonal elements from lambda, that is 8 minus lambda, 7 minus lambda, 3 minus lambda. Finding the determinant and which is equated to 0. Here we will have cubic polynomial. Thus we will have three roots of the equation. Finding these three roots by using the synthetic division or Horner's method. So we will have three roots, that is lambda is 0, 3, 15. So these three are called characteristic roots or latent roots or proper values or eigenvalues. For each eigenvalue, there corresponds a eigenvector. To find the characteristic vector or eigenvector, first of all, we have to take the characteristic matrix equation. So that is A minus lambda I of x equal to 0. So that is a matrix of 8 minus lambda minus 6 2 minus 6 7 minus lambda minus 4 2 minus 4 3 minus lambda. X is an unknown matrix, that is x1 x2 x3 equal to O, that is a null matrix or zero matrix, matrix of 0 0 0. Now let it be equation number 1. So using this equation, we can find the required eigenvector corresponding to the eigenvalue lambda. Eigenvector corresponding to eigenvalue lambda equal to 0. Just putting lambda equal to 0 in equation 1, we will get just putting lambda as 0 in this equation. And the system is equated to the null matrix or zero matrix. So we will have three equations. Now solving any two of the equations using cross multiplication method. So using cross multiplication method, and these proportions are equated to a constant k. Let it be k. So here the fractions, each fraction is equated to k. So thus we will have x1 is k, x2 is 2k, x3 is 2k. And taking in general k value as 1. So thus we will have x1 is 1, x2 is 2, x3 is 2, which is the required eigenvector corresponding to the eigenvalue lambda equal to 0. Eigenvector corresponding to lambda equal to 3. Putting lambda equal to 3 in equation 1, we will get. So in this equation, just we have to replace lambda as 3. That is 8 minus 3, 5, 7 minus 3, 4, 3 minus 3, 0. And the matrix is equated to 0, that is null matrix. So we will have three equations like this. Now we have to solve these three equations and consider any two of them, and solving using cross multiplication method, we will have three unknown values. These three are unknown values by taking k equal to 1, same as above. So thus we will have the eigenvector corresponding to the eigenvalue lambda equal to 3 is matrix of minus 2, minus 1, 2. Now eigenvector corresponding to lambda equal to 15. Putting lambda equal to 15 in equation 1, we will get. Again we have to put lambda equal to 15 in this equation, that is 8 minus 15, 7 minus 15, 3 minus 15, minus 7, minus 8, minus 12. So we will have equivalent matrix like this. Now the matrix is equated to 0. So we will have three equations. Solving any two of the equations by using a cross multiplication method, we will have three unknown values. The three unknowns are x1 is 2 and x2 is minus 2, x3 is 1. In general, taking k equal to 1. The eigenvector corresponding to the eigenvalue lambda equal to 15 is a matrix of 2, minus 2, 1. Hence the required eigenvalues are 0, 3, 15, and the corresponding eigenvectors of A are matrix of 1, 2, 2, matrix of minus 2, minus 1, 2, matrix of 2, minus 2, 1. Problem: find the eigenvalues and corresponding eigenvectors of the matrix of 2, 2, 0, 2, 5, 0, 0, 0, 3. Given matrix, the characteristic equation of A is determinant of A minus lambda I equal to 0. Just taking the determinant of the given matrix A and subtracting lambda from the principal diagonal elements of A. The determinant is equated to 0. Now solve this equation, the determinant, we have a shortcut formula. Don't tell to anyone. So it is very easy to find the characteristic roots using this equation. The equation is minus lambda cube plus sum of diagonal elements into lambda square minus of sum of cofactors of a principal diagonal into lambda plus determinant of A equal to 0. So here minus lambda cube, sum of diagonal elements. So here diagonal elements are 2, 5, 3. So that is 2 plus 5, 7, 7 plus 3, 10. So sum of diagonal elements is 10. Now sum of cofactors of the principal diagonal. So it can be computed like this, that is the minus of leading diagonal elements. Just Delete the row and column which contains 2. So we will have the submatrix 5003 whose determinant is 15. Now delete the again the row and column which contains 5, another principal diagonal element, that is middle element. So we will have the matrix of 2003. So computing this determinant, we will have 6. Now last one, principal diagonal, last element is 3. Delete the row which contains 3 and which contains column. The row and column corresponding to 3 are deleted. We will have a submatrix, that is a 2 2 2 5. So finding this determinant, we will have 6. That is the matrix determinant ABCD is AD minus BC. So these are the determinant values, that is the sum of linear minus of leading diagonal elements, that is 15 plus 6 plus 6 equal to 27. So it is the sum, just replacing this. And last one is the determinant of A. Finding the determinant of the 3 by 3 matrix, we will get 18 as answer. So it is the characteristic equation of the given matrix A. And solving this equation to find the latent roots. This equation, this 3 cubic polynomial is solved by using synthetic division or Horner's method. So solving this equation, we will have eigenvalues, that is 6, 3, 1. For each eigenvalue, there corresponds a eigenvector corresponding to lambda 1 equal to 1. So for lambda 1 equal to 1, consider the equation A minus lambda 1I of x1 equal to 0. So what is x1 here? Eigenvector, that is a matrix of x1, x2, x3. So equating these two matrices and solving any two equations using cross multiplication method. So we will have these three fractions like this, which is equated to k here. K is arbitrary constant. So x1 equal to like this. In general, we can take as k as 1. Eigenvector corresponding to lambda 2 equal to 3. So for another eigenvector, so we have corresponding to the eigenvalue lambda 2 equal to 3. We will find like this. That is, for this we have to consider the equation, that is a minus lambda 2I of x2 equal to 0. So subtracting the number 3 from principal diagonal elements, so we will have the equivalent matrix like this, and we will solve using cross multiplication method. So here we will have another eigenvector, that is x2 is k into 0 0 1. The fractions are equated to k, that is x1 equal to 0k, x2 equal to 0k, x3 is a minus 6k. And the total fraction which is divided or multiplied with minus 6. So we will get x3 by 1. So which is equated to k, x1 is a 0 and x2 is also 0, x3 as 1. So it is another eigenvector. Now eigenvector corresponding to last eigenvalue, that is a lambda equal to 6. So we will have a minus lambda 3 I of x3 equal to 0. Slight mistake is there, x3. This one is x3 equal to 0. What is x3 here? Matrix of x1, x2, x3 equal to null matrix O 0 0 0. Same as above, solving, that is using cross multiplication method, we will find the characteristic equation of the matrix, also find the eigenvalues and eigenvectors of the matrix. Given matrix A minus lambda I, just subtracting lambda from principal diagonal elements of the given matrix A, thus we will have A minus lambda I. Now the characteristic equation is a determinant of A minus lambda I equal to 0. Just finding the determinant and which is equated to 0. So thus we will have polynomial like this. So it is the cubic polynomial and it will have 3 roots. Finding these 3 roots by using Horner's method or synthetic division method. These 3 are 3 roots. The 3 roots are known as characteristic roots or eigenvalues or latent roots or proper values. Now for each eigenvalue, there corresponds a eigenvector. To find the eigenvector, we have a relation between a lambda x, that is ax equal to lambda x, or simply it can be written as a minus lambda I of x equal to 0 by the use of identity matrix I. Now for lambda equal to 1, just putting lambda equal to 1, so we will get the equivalent matrix, that is A minus lambda into 1 of X equal to O. Now the matrix A is reduces to row echelon form, that is interchanging R1 and R3. So we will have equivalent matrix. Now applying R3 goes to R3 minus 2 R1 and R1 goes to minus 1 into R1. So we will have the matrix like this. This matrix is known as the matrix is in row echelon form. So clearly the rank of the matrix A is 2 because the two non-zero rows are there. The rank is 2. So clearly we will have two equations here. Just we have to define the arbitrary constant k which is assigned to one variable, that is x3. So x3 is assigned to k and x2 becomes a minus k. Here we are assigning one arbitrary constant because the rank of A is a small r which is equal to 2 and the number of variables n equal to 3. Since 2 less than 3, just we have to assign one constant because n minus r is 3 minus 2 equal to 1. One arbitrary constant k which is assigned to one variable, that is x3 equal to k and x2 becomes minus k. Substituting these values in first equation, we will get x1 value. Now taking out minus k as common, so thus we will get x1. So that is x1 is a matrix of 1, 1, minus 1. Now taking lambda equal to 2, same as above, interchanging the rows and applying the row operations so that the matrix equivalent matrix becomes the quotient matrix can be reduces into row echelon form. So it is a row echelon form. Clearly the rank is 2 here. We have to assign one variable as k. Let it be x2 be k here. x3 is a 0 and x1 becomes 2k. Thus we will have another eigenvector, that is x2. Thus only one eigenvector x2 corresponding to the repeated eigenvalue lambda equal to 2. Hence the eigenvalues are 1, 2, 2. Hence the eigenvectors are x1, x2 equal to x3 equal to k into matrix of 2, 1, 0. Here don't forget there are two eigenvalues are equal here. So eigenvectors are also equal here. In general, we can take k as 1. So thus we will have three eigenvectors corresponding to three eigenvalues. The eigenvalues are 1, 2, 2. The eigenvectors are x1 is a matrix of 1, 1, minus 1. x2 is matrix of 2, 1, 0. x3 is also matrix of 2, 1, 0.